Hi, good afternoon everybody. Welcome to this fourth episode on the OpenHT Firmware development process. So, last time we tried and failed to get the microphone working on the Disco board. So we spent a bit of time trying to make it work properly, and in the end we managed to do that. So first of all, I'm gonna go through the code to show you a bit what have been done and what were the mistakes that we made. So I decided to move all the initialization of the peripherals, so the filter and the I2S peripheral, to the task microphone file, so nothing is handled by CubeMX anymore for those two, because it was just a pain in the end having to regenerate the code via CubeMX every time I wanted to change a parameter. So this is it, and then the loop. So we still have the event, so we wait for the event to trigger, and then we start recording the file, we start processing the data, and so this event is triggered whenever we have done half an acquisition or a full acquisition, and half an acquisition is the size of one block of data for the PDM filter. So I was pretty sure that at some point I saw the PDM reading pointer being modified by the PDM filter, which actually shouldn't be possible, so I don't know why I saw that. So I really thought that this pointer was being moved, but it was not. So also I had a problem with the DMA initialization that we use for the I2S peripheral. So let me show you that it's in this function, I guess. Okay, so here it is, and it was set to bytes alignment, so it was working with bytes instead of dual bytes or half words. And this was one of the problems that I found shortly after I stopped the last stream, and so with that fix already we had a voice that we could recognize, but it was sounding very much like an SSB voice, and so we could guess what I was saying at to the microphone, but it was really not good at all. And so the last problem that I had to fix, and which took me some time, was that indeed I had to assign the PDM reading pointer to this value after I'm done receiving the whole buffer. I thought that it was being modified, this value was being modified by the PDM filter, but it was not. And so it created a problem where we repeated every half buffer. So instead of writing first half and second half and first half and second half of the buffer, we only wrote the first half of the buffer. So it means that we lost half the data, and we repeated the first half to have as many data as needed. And so this is why it had kind of an SSB tone to it, because it was like, yeah, you have a all kind of frequency components appearing when you do that. And so that fixed it, and so I will now be able to show you how the voice sounds. So I have the micro SD card right here, and if I reset the board, so the GUI didn't move from previously, so you still have the PTT button, and so the PTT button right here saves the voice data. So just as a reminder, we process the PDM data as soon as it's created, then we store it in a sound buffer which is in the SDRAM. We have a maximum 2 megabytes of data, of PCM data, And once we have this PCM data stored and we release the PTT button, so the transmit button, then we go to this section where we write the data to a WAV file, and then we are able to read it back on the computer. So just for demonstration, if I press on the PTT and speak in the mic, this is Oscar November 4, Mike Oscar Delta. So the WAV file is now saved on the micro SD card, and if I insert it in the computer, this is what it sounds like. This is Oscar November 4, Mike Oscar Delta, which is much better than what I expected. So don't mind the first bin file, it's not being generated anymore. It's an old file that we use for debugging purposes. And screenshot, I mistakenly took a screenshot. Okay, so this is it, the mic is working. So we still have loads of things to do with the sound. We will have to send it to the FPGA for the RF transmission and so on. We will also have to do the code for the speaker or the headphones, because the sound has to go there, and I haven't figured out how it works yet, so it will be for later. I'm quite, I don't want to do more sound anymore for now, so what I want to do today is start working on an FPGA thing. So the way we intend things to work is that there is 128 megabit or megabyte, I don't know, NOR flash on this board. So let's maybe check what size it is. I don't know on which page it is. Okay, this is it. So let's see datasheet for this file. So I guess it's 128 megabits. So just checking. Okay, 16 megabytes indeed. Okay, it's a bit smaller than what I expected. Also, what we will need to do is check with the Lattice program what size is one FPGA image. We will need to know that. Also, what I'm already gonna check is the size of a sector. Okay, so it is 4 kilobytes. Okay. So I'm first let's create a markdown file in which we are gonna write down a plan of what we are gonna do. Hi Andy, doing fine, and you? Actually 16 megabytes, it won't allow us to store like loads of, it won't allow us to store videos or anything like that, but it's enough for a few FPGA images, and also we should be able to store few settings commonly used and so on. So like the state. So I think Jae already did that, because whenever you reset the board or reprogram it, the call sign, selected mode and frequency are kept, and so he already initialized the QSPI module and so on. to have access to the NOR flash. We'll just have to figure out what he did, where he wrote to the flash, and where we can write, and yeah, we'll do that. And yeah, okay, let me just open the correct folder. So it's gonna be right here. New file, and we are gonna code it. Yeah, new file, I said. Right here is fine. Okay. So one thing to note is first, whenever you erase a flash memory, you are left with all ones, only ones. So when you write to memory, you can only write zeros, not ones. So that's first thing. Second, when you erase the NOR flash, or any kind of flash usually, you can only erase by 4 kilobytes. So maybe we should first okay. I think this is better. Okay. So great. Now we are gonna go in the code and have a look at what does Andy do, what Andy, sorry, Jae. So memory information, that's not it. OpenHT hardware config, that's not it either. Where does that happen? Okay. Maybe we can see QSPI read reference from the project. Okay, in user settings.c. Get settings, you do QSPI read. Okay, so lots of commented out code. Okay. Let's maybe remove all the unused codes. We have some here. We have some more here. Sorry, this. Okay, I have no idea what this memory map is supposed to be. What interests me is to discover where he's writing and how it does that. Okay, that's a bit cryptic. Okay, let's have a look. So, no, not this file, this one, quad SPI, what does it mean? Oh, okay, memory mapped mode. That's okay, that's what I thought. So basically you do not have to say write to this area of the memory or write to that area. You just use the memory as you would in classical C code, and it automatically does the writings for you. Okay. Okay, let's maybe start a debugger and we'll have a look at the values of the different functions, the different variables, and see if we can make sense of it. So current address, So we also have this settings T structure, which is 10, 12, 14, 15. I guess it would be 19 bytes. Because this, I guess, would be a uint32, I guess. But we can have a look actually. So here, where are our settings? I guess there is settings somewhere that we can. Where is this one used? Custom UI init. Okay, user settings. Okay, so if I do add as a watch expression, user settings. Okay, I will try to have a look directly in the memory, if I can do that. I guess it is show view and memory, I guess. So 0x2 0000 C10. So this will start with 10 bytes equal to 0. So we have for a 10 bytes equal to 0, then TX frequency, which is 4 bytes to 0, and then RX frequency, which is 4 bytes to 0, and then but then mode doesn't tell us the size of it. Anyway, this is not very optimized, so let's first maybe go to this structure again, and we will try to align things a bit better. So we want first to have the uint32 values so that those will be aligned. So in case you don't know, memory really likes when you are aligned on basically on the lines that you see here on the screen. So if you don't do that, it's gonna work, no problem, but it has to do more operations. Basically, it's gonna have to, so if you want to read a value which is across the boundary, like for example in the case of TX frequency where it was, you had 4 bytes, then 2 bytes, which are half a word, and then you had to read this half of this cell and then the first half of the next cell. So you have to read twice and then do the operation to basically to merge that together and have one 32 bits value. So if you do it like this, it only has to read once and so on, so it's better. Then I also guess that it's gonna have an issue with, so if I move that, it means that it's gonna not be able to read data from the NOR flash, I guess, because it's gonna fill the TX and RX frequencies with what was supposed to be the call sign. And so the mode, I still don't know. I think the mode would be 32 bits. Anyway, let's keep going and read. Okay, so we have 2C010, so we start here, and then we have call sign. Then we have, so the call sign is 6 characters long and then 4 times 0, so we go up to here, I guess, and then we read. Oh, okay, so it did some yeah, it automatically did some alignment things. So those 4 zeros should stop here, and so the next value, the TX frequency, should start here. But it automatically inserted 2 bytes that aren't used, and then it stores the frequency on the next aligned word. So 2 next words are this, and so after that we have this one, and yeah, it doesn't tell me actually the size of it. Size of settings T is 24. So, oh, we have audio volume too. So maybe this one is set to 1 byte. Okay, let's oh, you know what? Maybe what would be useful first would be to check if we have a way to print things to the serial ports, VCOM. So this can be done easily here. No, sorry. Right here, and have a look at the write function. Oh yeah, okay, IO put char. Okay. Okay, so we don't have any function which allows us to print for now, and we have to actually just implement the IO put char, and this will allow us to do that basically. So let's do that in the main function maybe. So where should we place it? Where is the function where I can write code? Oh, it's already there actually. My bad. So that means that if I go okay, getting lost among the files. It's in here, and if I do So like this, I should be able to open the shell. COM5. Like this. Move that here and this one here, and go. Need the board. So go. So we will do things with the LEDs and the printf. And okay, nothing. Why is that? That's quite frustrating. Why is nothing being written? Is the UART being initialized correctly? I guess so. Okay, let's... Okay, so we do go here, and we want to write data from the pointer. Okay, and we have to write 55 bytes. Let's just... Okay, well, at least we have our answer, which is that it is 1 byte for the mode and 20 bytes. So we, just by moving around the frequencies, we saved a few bytes. So we are now 20 bytes instead of 24, I guess. Okay, but then why is it that it doesn't appear here? It should be showing up, but it does not. Why would that be? Okay, let's check maybe that the UART3 is set on the correct pins. I think it should be okay, but just check nonetheless. So ST-Link RX and ST-Link TX. So PB10, there shouldn't be any pull-ups here, I guess. I think, I'm not sure though. Let's see if things improve. Otherwise, I could have a look at other codes. Also, I could have a look at the UseArt to see if it's configured correctly. Which it seems it is. Okay, so we should now be able to see if things appear in the terminal. No, it does not. Why is that? Very confusing. Maybe let's try again and see what goes on here. No, it seems to be transferring bytes correctly. I'm trying to think if there is anything I could check that could tell me very quickly how to fix this. Okay, I won't be very long on this one. I don't want to lose loads of time doing this. So let's just go to this project. We close that one and see how it was configured in that one. Okay, and I think that it was in the main. Oh, sorry, the main of this one. So this file, and I think there is the right function here, which is exactly the same. Yeah, the code is based on this one. So, that's very strange. Oh, it does have a pull-up here. Okay, why not? Does this one print anything to the shell? What is it now? Ah, of course, yeah. Hey, why is nothing going on? So this is the LVGL disco settings. The LVGL port for this board, which I updated and should be working. I have no idea why. So okay, let's close this topic for now. I'm gonna have a look later on, but not now. So anyway. No, sorry, that's not what I meant to do. Debug, and so we are gonna have a look at the addresses at which you write. Okay. Okay. Let's just remove this breakpoint. Don't need it. And okay. So we initialize the settings. So I guess it means yeah. What does that do actually? Okay. Current address. Oh, it's So I guess that using the memory mapped mode, the 16 megabytes of the NOR flash are mapped from address 9 blah 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 to 91 blah blah blah. And so if you want to write at 9 blah 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 1, you have to use the BSP QSPI read at the address 1. Maybe let's just check. This should be 16 megs, I guess. Yeah, okay. Indeed, that is indeed 16 megabytes. Okay, that my assumption seems to be correct. And so we might change these settings later on. For now, let's do an assumption that this code is never gonna use more than 4 kilobytes at a time. So, hey, I'm glad to know that you learn from these shows, Andy. That's the goal behind it. It's fun too to do streams because yeah, you meet people, you discuss and so on. It's entertaining even for me sometimes. But then most of all, the idea behind it is that I would like everybody to be able to understand what we did and how we did it, because open source software is great. Open source hardware is more difficult to do, but very nice too. But I guess open source knowledge is is even better. So I don't pretend that I have the best knowledge in all of these things and codes and so on, but I'm ready to share whatever I can share. Okay, so let's go back to our memory map. So I guess it's written in the datasheet actually, the number of sectors that we have. Well, I can compute it actually. So it is 16 megabytes divided by 4 kilobytes. So we have 4096 sectors, which is plenty for what we want to do. So what we are going to do is try to assign memory areas to specific settings. Hi Bastien, how are you? Okay, you're a hardware engineer. Great. Hi Wojciech, just to say hi. Oh, you missed the bit where I had the sound on for the microphone. Yeah, I'm actually an electronics engineer too in Belgium, so I get it for the hardware part. The software is my spirit is that whenever you do hardware, at some point you will have to have some knowledge to use your hardware, and sometimes just develop tools needed to support your hardware. So that's also one of the things that interests me in the software things. Okay, map. So I think we are going to allocate 2 sectors for the user settings. Why 2 specifically? It might be because we need the room of 4 kilobytes times 2, so 8 kilobytes, but that's not really why. The way we are gonna do is that we are gonna write, so as I said, you cannot erase just a few bytes. You have to erase 4096 bytes in a row. Also, one of the very important things on NOR flash is that you can only erase it a certain number of times, and usually it's about 100,000. It might seem like a lot, but if you change your settings 10 times a second, so imagine a naive setting where you write at the beginning of the page and then leave the rest of the page blank, and every time you change its value you erase the page and rewrite. Then you can only write 100,000 times. If you do it like even once every second, that means that you can only do that for 27 hours, 28 hours nearly. So about a day. And after that, you have to forget about this page of flash memory, because it's gonna have problems and not gonna erase properly, or not gonna write properly, or read properly. It's got all kinds of problems. So either you go to the next page and then you will lose 4 kilobytes of data every day, which is a lot, or you can simply write. So the way we are gonna do that is yeah, this is the NOR flash handling, Wojciech. So the structure that we are going to use, it's called an emulated EEPROM. even though I think we do have some EEPROM here, but I don't know where and what. So yeah, the way that we are gonna do that is each value is gonna be stored in a table. So I hope I remember how we do tables in Markdown. Maybe I don't remember. Ah, that's it. So that means that, for example, I want to emulate an EEPROM. So let's say I want to write the TX frequency. So TX frequency is gonna be address. We can even do that on a full half word, for example. It's just an example, okay? The TX frequency is going to be stored on 16 bits. The address is going to be 16 bits too. So that means that whenever we write, we want to write at the address 1 the value 1, 2, 3, 4. So we write address 1 value 1, 2, 3, 4. But then let's say that we want to update the value of the TX frequency. So maybe we want also to have the RX frequency, let's say. So we will have so this is what it's gonna look like in the memory. Maybe we can also add another field, which is hardware address, which is gonna be quite long, I think. How many zeros do I need? No, it's not that one, that one. Okay, I had one too much. Zero. And then like this, I guess. And sorry, just tidying things up so that we can keep the readability. And somebody is drilling in the wall. Great. Is it picked up by the mic? I don't know. So do you understand? I hope you understand at least what I'm showing here. So this is the hardware address. So for the microcontroller, this is where this value is stored. So at the address 90 blah blah blah, we write the value 1 and then the value 1, 2, 3, 4. And so this is the address, and those are written to memory. This is another address, and those are written to memory. So what happens when I want to update, for example, the TX frequency? Then I'm gonna have another entry to the table, which is 0x90008. And now I'm gonna write address 1 again. And now the value that I want to set. I just set it like this. So whenever I go through the table, I'm gonna see that the address 1, or more than an address, it is more like an index. Index 1 is set here at 1, 2, 3, 4 and here at 4, 3, 2, 1. So how do I read it then? It's not very complicated to read it. You just have to do to go through the table in reverse. So you will go so this is this is not that one actually. This is out of the chip, so let's and this is not gonna be F, this is gonna be yeah, okay, this is gonna be it. I'm doing so I'm gonna write, what I want to do today is be able to import the binary file of the FPGA to the QSPI memory NOR flash, and maybe start writing a bit of code on how to send that data to the FPGA. So I do have an FPGA, the same that we are gonna use on an evaluation board. So let me grab it. So this one, I'm not gonna use it today, definitely. And I don't know where I'm gonna have the proof of concept in my hand to test the code, but I do have the datasheet available. And so I'm gonna try using that to write first bits of code. But I don't know what we are gonna be able to do today or not, so let's see. So I said, so to write the memory, to read from the memory, we are gonna read from this address and then go upward. So that means that whenever we read address FFFF, it means that, so remember, when the memory is erased, it is all ones in the memory, so FFFF. So you read FFFF and then you go upward until you read not FFFF, and actually when you read until you read the value that you're looking for. So we are gonna have FFFFs everywhere in this page, and then we are gonna arrive at this address, which is gonna be set at 1, and this is the value that we are looking for. So we'll read this value, and then we get it to the user. And this is how you read from emulated EEPROM. Also, I think that we are gonna need we might need one more page. So we are gonna need, so yeah, yeah, I'm going a bit too fast here maybe. So that's the way you read and write from emulated EEPROM. And so you see that you only write and you do not erase, except when, of course, you have filled the memory with, so the whole page is updated. What you have to do then is go to the next page. Yeah, this is actually not correct. This should be, let me, yeah, okay, 1000. This is more like it, so. Okay, this is the end of the sector one, so let's oh, this is a comment. Very convenient, but let's hey, my table is looking nice. So then we are gonna have this, which is gonna be like that. Start of sector 2, end of sector 2. It's gonna be like that. Okay, and of course we are gonna okay, this whole sector 2 is empty. So when the first sector is completely full, you are gonna read it backward and read all the values that are unique. So you are gonna read it upward, and every time you find an address that you haven't found already, you write it to the sector 2. So that way on sector 2 you are only gonna have all the unique values condensed. So if the first sector is filled with only addresses 1 and 2, for example, so indexes 1 and 2, then you are only gonna have 2 values on the sector 2, and then you can start again the whole process while you erase the first sector. And that way, yeah, that way you can easily decide, you can easily, sorry, let's drink. Okay, so this is a way to emulate an EEPROM in a memory that you can only erase by 4 kilobytes. I didn't invent anything, of course. This is an emulated EEPROM, EEPROM. And this is very common and described everywhere on the internet. So nothing new, just explaining to you. Great, so that's what I want to do. Actually, I don't need sectors allocated for the memory management. I thought that I would need it to remember which page is the active one, but it's easy. The page which is the active one is gonna be the page where you don't have Fs everywhere, basically. And the first line is not FFFF. And if the 2 pages have FFFFs, that means that the 2 pages are unused, and so you can simply pick whichever you want. Okay, so I said we have 2 sectors allocated for user settings. And then we are gonna have 2 sectors Yeah, let's resolve 4 sectors so that we don't have any problem or anything. 2 sectors allocated for the FPGA images index. Which are going to be used as an EEEPROM. So basically what I will want to do is have a first byte and 3 bytes. What's the value that I can store on 3 bytes? So I can store exactly 16 megabytes. Is it? I should be able to oh yeah, no, let's not do that this way. Let's maybe I can actually just 2 bytes for the image index, or yeah, and 2 bytes on which we will be able to store the sector at which it starts. Because for the FPGA images, we are gonna work by sectors, because those are way too large, so they maybe do maybe like 1 megabyte in size, something like that. So it will span across sectors. We can't ever use any kind of EEPROM like settings. So we are just gonna store the number of the page at which it is beginning. And so let's say, for example, that I want to store an image which is like so 789 kilobytes. So 807 bytes. Then I would have to use 197.25 sectors, so basically 198 sectors. Oh, but I would need maybe then I can do something else, because we need to know the size of the image in bytes. That is very important. With 4 bytes, we should be able to store more than needed. So each image that we store is gonna use 2 kind of lines of memory, if you want, from the view that we had here, which is here. Yeah, can we? Okay, like this. So if everything is one, oh no, yeah, it's, sorry, getting confused. Each image that we store is gonna take 2 words of memory for the index storage. Okay. We should start doing that. So, oh, I've been streaming for more than an hour already and we did not do much. Well, we did not do much code, but we had a look at a few things here and there, so still making progress. Okay, what is this end pattern? Ah, okay, beef. Okay. Oh, I see. Hmm. Okay, maybe we would need to I don't like modifying code that I didn't write. Okay, let's go to the IOC file. And we are gonna create a new task, which is gonna be for the FPGA. It's gonna be normal priority, I think. Let's allocate a bit of stack entry function. Then it's gonna be okay. Hey Jay, just a simple settings handler. Yeah, no worries about that. It's just that I'm having a hard time understanding what you did sometimes. It's always like that when I didn't write that. I will modify it maybe, but not right now. Okay, now that you're here, Jay, I'd like to ask you a few questions. So I would like to add a button to the GUI. I don't know if you are able to do that or if you want me to do it. I would need a way at some point to be able to trigger the loading. So what I want to do is have the FPGA binary images on the SD card. And when you press a button, you read it and you load it to the NOR flash. You think it's possible to do that like that? Sorry, why did I put microphone is FPGA? Great, and source, new source file. Okay. Oh, you're away from the computer. Okay, no problem. So first thing that we are gonna have is how did I do it in the microphones task? Okay, like this. I could repurpose the PTT, that's true. I don't need it now that I did that. Okay, trying to think a bit. So, oh, if I touch the M17 logo, it does a callback. Nice. Let me check that. Oh yeah, oh yeah, okay, the about page, yeah. Oh, what the hell is happening? I'm trying to... Okay, all right. Yeah, I'll check later what I do with that. For now, we have the task FPGA. It's not that the touch went crazy. I was trying to use the keyboard, but it's not. It's very small and not very. Yeah, it was a bit hard. Anyway, I just because I changed the way this. So just so you know, Jay, I did some changes in the user settings file. Basically, I rearranged these. I can even do like... no, it's not gonna change anything. So I put the two 32 bits variables at in front because it avoids wasting space, because what the compiler does in that when you first put the call sign is that the call sign is 10 bytes, which means that in order to have a multiple of 4 bytes for the alignment, you have 2 extra bytes in the end which are unused and which are zeros. So that means that you had 10 bytes for the call sign, then 2 unused bytes, then you had bytes used for the TX and RX frequency, and then bytes used for the audio volume and the mode. And so this was basically you lost 4 bytes, and this way you spare 2 bytes at the end of this, which are used by this and this, and yeah. So yeah, it's always the syndrome where you are in front of a white page and you are wondering where you should start. Maybe we should define a few. Okay, let's just new header file. And do a nor map. In this file, we are going to be able to map all the settings that we want in the for the nor flash. I'm gonna grab a few defines that you did. So mainly those. No, maybe not these. I want. I also want to copy this. Ok, alors... No, I don't want... So if I go here, I should be able to include nor map. So this, that can erase. Okay, so I guess the +4 it's used to store the AND pattern. Okay. Syntax error. Why? Ah, yes. What is happening here? What? What the hell? Ah, silly me. That's why it wasn't working. Definitely better. Still have a problem here. It seems that where is it precisely? Console. start task FPGA. Yeah, I guess I have to okay. Start task FPGA. I guess I gave the wrong name actually to the function. So yeah, okay. So now it should compile correctly. Okay, great. So what would be the most convenient way to store? So I want to, in this file, I want to store all the macros or variables, let's say, in which I'm gonna remember all the how I managed and I mapped the NOR flash. So I'm gonna have two sectors for the user settings. Maybe maybe I can also store on the addresses. Yeah, for being too erased too frequently, you mean, Jay? Yeah, don't worry about that. It happens that I had some times today, but usually on the weekend I'm not available much, so no worries. So I'm gonna store a few addresses just like this. Okay. Well, this I will modify this algorithm at some point, but not right now. So this way we can just modify the sector numbers, and these values should be updated automatically. I also want 'How many sectors should we reserve for the binary files?' Let's reserve half the memory. So that would mean 2048 sectors of 4 kilobytes. It will be 8 megabytes. And then we have still memory left available for whatever. So what did I get? 2 bytes for the image index. So that means like this. And let's write Isn't Oxygen enabled on STM32 QAD? Just checking quickly. I always forget about. Ooh. And this should be constant, and this too. Isn't there any defines that? Just let me check something quickly. Yeah, okay, exit success and exit failure, those are the ones that I want to reuse. Okay. Okay, so the way this is gonna work is that first we have to include FATFS, of course. Voilà, sorry. What are the default values? There is no generic error, it seems. Okay, well, anyway, let's actually, I don't need to assign a value. I will do it right here. I'm just gonna have the FATFS documentation on the side. I think I downloaded it. Yeah, right here. Okay, perfect. Okay, so yeah, we want to read the file only, not write to it. And also we want it to fail if the file does not exist. Maybe we actually want to return an F results. I don't know. Maybe not actually, because we are gonna have different kind of errors. Return exit failure, okay. Okay, I think we are gonna have to write triple EEPROM library quickly. I don't really feel like doing that right now. So maybe let's write a prototype. Can't we? So we want, first we will want, so because the library will be used to store so we will use the same library for different EEPROMs. So we have to define a structure. So the handle is gonna be used to store this, okay. We will want for now, let's only allow some EEPROMs of 2 pages, including the one to swap the data. So yeah, so we will want start address. Okay, we will want some more data to be continued. This is just a prototype. Then we will want we will want also the size of an entry in the EEPROM in bytes. So remember, like I said, so in the first example I gave, each entry, it's only 1 word, so 4 bytes. But here, each entry is gonna be 8 bytes, 2 words. So this is gonna be important. We will need to store that. And then we have the entry size, and we have the address size. Then we of course are gonna have the Sorry. Data size. Which, well, no, we don't need to do that basically because it's gonna be the entry size minus the address size, of course. Otherwise, it's not gonna be possible. Okay. Write data. We are gonna need an EEPROM handle, and then okay, so so we want to be able to write data and read data. Trying to see which functions we could use. Maybe okay, so I think I'm gonna need an initialization function. So this function is gonna check that the data in the sorry. Soon gonna stop the stream, I think. So this initialization function should check that the handle here is coherent. So we have an address and page size and so on, which is logical. Also, I believe that we are gonna have some kind of internal data in the handle that we are using, that we will use to remember which is the active page and so on. So initialization function. Okay, and finally pointer to the okay, like this. This should give us enough for now to get started. Anyway, I think that's gonna be it for me today. So it's been a bit more than 2 hours, which is great. Okay, so I hope that those who were here today enjoyed the stream. So no major failure today, like previously. So we saw that the microphone is working. We started working on the EEPROM and the NOR flash and the FPGA thing. And still a lot of code to be written. I won't be able to possibly do everything on stream. That would be way too much. I do have a life too. And so yeah, thank you for being here today. Don't forget always the Discord server that we have for the M17 projects. And I hope that yeah, we will have this proof concept working pretty soon. So yeah, thank you everybody, take care.